After Johan's talk, I wanted to talk about complexity instead, but I don't have that. So if anybody wants to talk about complexity in general at lunch or whatever, that's a topic I've worked on over the last couple decades. So it's a good topic, especially for people who are doing technology deployment of any sort. Okay, so what is this about? Why am I talking to network people about machine learning? And I'll just give the high level thing right here. This is, what's going on in machine learning is the most astounding thing I've ever seen in tech. And I've been in tech for like almost 30 years now. And it's gonna affect you in dramatic ways. But right now, what I'm gonna try to do is have a little fun with this and show you some of the cool things that are going on and then how we might apply all this stuff to networking. In fact, my little group at Brocade, we have a tiny, tiny AI lab, which consists of me and a few other people. And we made some really interesting machine learning stuff going on to do sort of basically DevOps automation. But let's take a look at this. So, this picture here, you can see all kinds of pictures like this on the web, and people always think, well, if you're doing machine learning, it must be some kind of fancy AI stuff, right? But what it really, so that's what my mom thinks I do. But what it really is this. People come and give you data, and you go, what is this stuff, right? And you're all confused. And the reality is what you do is this, math. That's what it all comes down to. And so I'm gonna go really easy on the math part here. If anybody's interested in math, it's my favorite thing. If anybody's interested in the math behind this, I'll give a little of it to you, but just talk to me about it. It's unlimited as much as you want. And these slides are online there, or I don't know if they're gonna be distributed, but you can have them anyway. Okay, so goals. Let's take a look at the current state of the art in machine learning. See if we can get a basic understanding of it in like 15 or 20 minutes. That's like impossible, but let's try. And see how we might use it to do something interesting in a network automation setting. All right, and really it's all about math, but I'm gonna stop with that, right? Just a little bit. So what's it all about? This is my agenda. What's it all about? And what is ML really? I mean, what is it? How many people know what it is? Really? Yeah, okay. I didn't either when I got into it, but I learned. Some tools for DevOps and maybe a little bit about the future. I don't know if we can get through this in the time we have left, but if we don't, just track me down. So ML is kind of about getting knowledge about your domain, like we heard earlier about configuration systems and things like that. ML is kind of about this. But when you start thinking about it, where does knowledge actually come from? For humans, right? So the first thing is we get it from evolution, right? It's bound up in your DNA, and that stuff tells how to make you and other kinds of things. You get it from experience. You have experiences, and then you learn things, and you get it from experience. And then we get it from culture. Culture is one of the things that allows us to propagate knowledge over time. And so these things are the ways that we used to get knowledge. But this is the new way we're getting it, right? And if you listen to somebody like Jan LeCun, he's the director of the AI labs at Facebook, and one of the kind of the fathers of all this stuff. This is what he says. So in the future, it's all about machine knowledge, right? And one other thing I wanted to mention to you here is that if you go across or you go down, there's many, many orders of magnitude in both speed and volume of knowledge that you get. So evolution is a lot slower than the experience you get. The experience you get isn't as fast as the experience that culture gets in general civilization. And what machine learning is going to do is just blow all that stuff away. It's already doing that. So that's what's going on there. So how could a computer actually get knowledge? Well, you could fill in the gaps in your existing knowledge. Actually, some of the automation systems try to do this in an ad hoc fashion. In machine learning, these are called symbolists, and their actual technology is called induction. You could try to emulate the brain. The brain's kind of a good learning thing. These are the connectionists and deep neural nets. Those are the things that are making your self-driving cars and stuff like that. You could try to emulate evolution. Evolution might be a better way to learn. It made brains and you and everything else, right? And those are called evolutionaries, and they use something called genetic algorithms. Or you could try to systematically reduce your uncertainty about the world, because you're learning stuff, it's inherently probabilistic, so you might try to reduce the uncertainty, and that's all about Bayesian inference and things like that. And then you could try to notice the similarities between what you know and what you saw, and that's like reasoning by analogy, and this is called kernel machines or support vector machines, or the technology that does that. All of these things are kind of like different schools of machine learning. Okay, so that's just a little bit of what is going on there. So what's all this about? Well, you know, I don't know about you, but I see a lot of excitement around what's called analytics, but I don't know what analytics are. And a lot of excitement about machine learning. So what's analytics? I saw this chart. This was some Gartner something. It kind of does tell you a little bit about what's going on, which basically means that what you really want to do is you want to work over here, where you can predict the future. That's the real magic of machine learning. You can predict the future a little bit, and that's what we're trying to do. So there's another way to think about it too. By the way, one of the things we did when we started working on this for networking is we work kind of like in the management plane. And the main reason for working in the management plane and not the data plane or the control plane is because the feedback loops are longer, so it's just easier. So this is a management plane perspective, but you can kind of think of the way it worked. I mean, how many people use like expect to do screen scraping? You know, yeah. So that was kind of CLI screen scraping. Then you got scripting on box, and then, you know, whatever, controller architecture, whatever. But basically, it just kind of moved to the right over here. But you could apply machine learning to all of this stuff and do some pretty interesting things. So that's kind of this is kind of how we were viewing it. Okay, so what is it about? Why is it machine learning? Well, so deep learning is a kind of machine learning, and I'll explain what it is in a second. But it's what's enjoying this great success. And it seems like it's an overnight success, but it's an overnight 40-year success. But the number of use cases is it's out of control what's going on. These are these multi-layer neural networks. So they're just big trees of what are called artificial neurons. So it looks like this. On the left, I guess it would be on your left, there's an input layer. That's the piece of data you hand to the thing, and it transforms it in such a way that it can either classify or compute a function or something like that. And tasks that you might think of as perceptual. What's perceptual? Well, vision, language, audio, all that stuff that you do, smell. Those are reaching what are considered to be superhuman performance levels. So what does that mean? You have a standardized benchmark. Human can get this kind of error rate. I can write a program now that does better. That's superhuman. Networking in these non-cognitive domains, anything that's not cognitive, is really lagging, although this one fellow at the IETF sent me this URL of some papers they did worked on a long time ago that learned filters in the data plane. So maybe. But networking is a new and recently active domain for this, because there's a lot of us who are in networking, and there's a lot of venture capital available for anything that says it's machine learning, so there's a lot of activity. So I got some pictures. So see these bounding boxes? These were learned by a neural network in a technology called convolutional neural network. By the way, I didn't see the Academy Awards. My wife told me this was like at the Academy Awards. But this is object recognition. Somehow somebody wrote a program that noticed that there were faces in there. And you see those bounding boxes in your cell phone or whatever every time you take a picture, right? So this is object recognition. But it goes further. There's actually auto captioning. I don't know, has anybody seen that, like on Flickr or anything like that? You know, you put some pictures in Flickr, and actually Google and Facebook have this too, and it comes back and captions the picture for you, plus develops this hash that you can use to search on the words and the picture itself. So it's kind of nice. And you can sell better ads if you have this. Now this is interesting. Why? For us. Because network use cases are going to use the same technology. This is learning technology. It's really not domain specific. So the same technology is going to be used in how you configure your routers, how you monitor things, how you do everything. Here's a kind of a cartoon how this auto captioning thing works. Basically, you have an image. You have a deep convolutional neural net. That's the fancy term for what this thing is. It segments the picture into whatever's in it. And then you use something else called a recurrent neural net to generate the language model and just spit out something like this. So if you get on Flickr or any of these places, you can give it a picture like that, and it will spit out things like a group of people at an outdoor market. That's pretty impressive, right? I mean, I think so anyway. How about this one? You think about self-driving cars. Hey, how many people saw the Tesla stuff today? So Tesla upgraded all their software, right? And now their cars are self-driving, or almost, semi-autonomous. What do they call it? They call it, there's a name for it anyway. So it's all over social media, but it's using the same technology. So this is the Google car. I'm not going to buy one of those. I'm going to buy one of these, or the newer one, right? But they're all using the same technology. Now, what is that technology? Oh, let me show you this. I don't know if I can make this work. I always have trouble with this, but I'll try. What? Let it load. Don't touch it. Click it once. No. I think I have to put the cursor on it somehow, if I can only find the cursor. Oh, yeah, I got it. Thank you. Okay, so this is not my company, but this company called Mobileye builds these parts, and then they OEM them to Tesla. So Tesla's having these parts. I'm going to just show you what these guys can do. They use the same technology, by the way. All right. You might be able to tell from this that I don't embed a lot of video in my talks. Oh, there we go. Is it actually going? So you don't have to hear the video, but the audio. But what I want to show you here is this particular product is collision detection for pedestrians, right? So what this thing can do is, see the bounding boxes? It's using that same technology that's in your phone to basically convolutional neural nets to detect this thing right here, and give you 2 seconds to claim of pedestrian warning. By the way, my wife said, "Why is that guy looking down when he's driving?" But, you know, it's the idea. But this is just a component of what a self-driving car can be, right? Now, it's more than this, right? Because the entire industry is undergoing this change, the automotive industry, from what they call nuts and bolts, they assemble cars, to intelligent technology, right? And so the car is now a platform for intelligent technology, and that's where the battlefield is, right? Well, if you think about, like, say you're an equipment vendor in the network space, nuts and bolts is really roughly equivalent to speeds and feeds. And the battleground is in intelligence, not in nuts and bolts. So Toyota put 40 million into this a couple weeks ago. They have to have this because they're going to compete there. How about Apple? Same thing. So you can see that there's a lot of activity around this. But how does it work? Okay, well, just think about your brain. This is the brain of a macaque monkey. Unfortunately for macaque monkeys, they're kind of like humans. So a lot of physiology gets done on them, and you can't really do this while they're, well, when you're done doing this, they're not in that good a shape. So, so here's the idea. There's a part of the brain called V1, and what V1 does for you is it's an edge detector, right? It detects edges in its orientation, right? And then later on in V4 and V2, what happens is those get composed into shapes like round, square, whatever. And then a little bit later, you get high-level objects like, oh, there's a face, right? And so what you notice here is that simpler representations get built up into these shapes, or things like that. And then, of course, later on in your brain, you can do stuff. But this is how it works. So the idea here is that these things are hierarchically arranged and composable. So now, how does your car see, or your camera? Well, it does it the same way. This is a convolutional neural net, and basically what it does is it takes patches of the image and, just through these processes, it starts to understand them, and then at the top of it, it goes, oh, it's a dog, right? And it does it in the same way. It composes these smaller, simpler parts. And you can see here, like, if you have this image of Sarah here on your right, the first part of the network finds the edges, see their edges and their orientation, and then maybe it finds ears and noses and stuff, and then at the top it puts it together and figures out it's Sarah. So they're composable, right? Here's some URLs if you want to read about it. But there's more stuff going on. Skype, well, this is old now, but Skype has real-time translation. So you could Skype somebody, it'll translate theirs to, whatever, Chinese, and you'll hear it in English. You think that's nice? I do. This is even more impressive, maybe. So there's a company, this is not the only one. There's a bunch of these companies that use this technology to try to determine people's emotional state, right? That's why the company's called Emotion, right? And what they do, here's what they do. They use the image recognition technology, same stuff your car is using, same stuff your network's going to use, by the way, eventually. And they can tell if people are happy, sad, surprised, angry, whatever, with some probability. You might think, well, that's a little creepy, and it is, but that's what's going on. And by the way, this is how this works. Facial key points, right? So this was in science. There's a whole issue of science covering this, but basically what you do is you just decompose the face into this psychological model, and you can do that now that you can do this facial recognition stuff. And maybe when you go to your psychologist, he'll have this sitting on his desk, and he'll look at you while you're doing whatever you're doing, and they can tell something about your internal state. This is also used for advertising. What do you call it? When you do a Super Bowl commercial, you get a focus group and then you interview them afterwards. Now they use this technology and you don't have to talk to them. You just know what they thought, right? With some probability. And everybody's in this game, Twitter, They open their own, everybody's opening their own AI lab. So why is it all happening now? Well, before 2006, people thought these deep nets couldn't be trained. So why now? There were technological breakthroughs in 2006, learned how to train these things. So this has solved a technical problem. I can explain it, but it's like the butterfly effect, Step on a butterfly in the 1,000 years in the past. I can explain, but we can do it later. These are the three guys who did it. Jeff Hinton, who's now at Google and Toronto. Yoshua Bengoi, who's at Montreal. And Jan LeCun, who was at NYU and is now the director of AI at Facebook. And they're students. They have fantastic students. There's a really nice article of their journey through all of this, the 30 years they've been doing it there. If you want to read it, it's pretty interesting. So the first thing is we got these theoretical breakthroughs. The second thing is compute, right? Basically CPUs were millions of times too slow to do this 10 years ago. The other thing is we have parallel processing algorithms, Hadoop, whatever, MapReduce. And we have GPUs, and now people are saying, well, we could actually use FPGAs for this. So even on the more cutting edge than this is FPGA technology. And then data sets. To learn, you need data. Before, the advent of the hyperscales, you didn't have this kind of data, and now they do. And by the way, that's why everybody's at Google, Facebook, Baidu, or whatever, because you need not only the compute resources, but you need their data to make this work. And there's an alternate view of history from Jürgen Schmidt-Huber, who's a really interesting dude. If you just search for him on YouTube, you'll find some of his stuff. He's pretty funny. But he wrote some rebuttals to their article about this in Nature. It's a kind of interesting thing because it's going on right now. All right, GPUs, you can get those everywhere, but it turns out that things like NVIDIA, that used to be a graphics card company, is now a deep learning company because you need you need a bunch of cores to train these things because they're massively parallel. And there's all kinds of open source code to do it. And it all has CUDA or OpenCL built into it. So it's really nice because if you write code that to do this, it'll sense whether or not they're GPUs and use the GPUs. Yeah, and you can even get them on Amazon if you want. So what about networking? We're here at a networking thing. Well, this was in Nanog 64. Somebody gave a talk, and of course they said, just sprinkle some machine learning, dust on this, and everything will be cool. But everybody knows that, to deal with a massive amount of data that we have, we're going to have machine learning. There's just no other way to do it. This was from Anis and Josh's talk on OpenConfig, right? And of course, this thing's a machine learning thing, right? And then here's the pointer to it. And then somebody's trying to start up a machine learning for networking working group in the IRTF. So it's the obvious kind of thing that's going to happen. Oh yeah, and OpenNFV. So in OpenNFV, they have this thing called the predictor, right? What is that? Well, that's a machine learning thing, but this whole thing is. So how is that going to work? I asked the guys who wrote this slide, how does that work? And they go, well, we don't know. We're just going to, So there's, networking people are starting to understand this. So now here's the thing that you can kind of imagine, right? So first, one shift that's going on is we're starting to envision our networks as just big sensor networks, right? So every counter, every SNMP, MIB object, everything in your Yang, in your Yang model is a sensor now, right? And so every sensor is kind of a dimension in some giant multi-dimensional vector. So this means that the network is actually builds this high dimensional vector space. And then you get these records out of your network that look like that. And there's this cursive dimensionality thing. I'll tell you what that is in a second. But guess what? This is ideal for using deep learning techniques. It's perfect, right? So all we have to do is figure out how to clean up our network data. That's a really big problem because network data is just ugly. It's dirty and it's really noisy. But it's the right thing. So imagine you could do this. You have some interface somewhere, it flaps, and because you've done this analysis, what you know is that the CPU utilization somewhere is going to spike and it's going to black hole something. You could learn this kind of stuff. So you could predict that. It's kind of interesting. You can do that and a lot more. Oh yeah, and obviously consider the implications of this in the security space, right? If you could predict this, or if there's some signature in this high dimensional vector space that you can't see of this kind of attack, machine learning can find that. By the way, that's one of the things machine learning is really good at is understanding high dimensional spaces. Like for humans, I can kind of envision 3 dimensions because I kind of walk around in it. Some people could envision 4 dimensions, but I don't know anybody who could draw a picture of something in 5 dimensions. There probably are something. I mean, how many people can really do that? I certainly can't do it. So here's the dimensionality thing. Machine learning is really good at understanding these high dimensional spaces. And by the way, the signals that you might want to find are embedded in this high dimensional space, and you got to go search for those. And humans can't do it. We don't have the ability because we evolved in a 3-dimensional world kind of, and these things are hundreds and thousands of dimensions or millions in some cases, and so humans aren't good. So a dimension, informally, it's a direction, but it's kind of like a feature of your network. You think about it as a feature. So what's an example? Well, these are things that have been worked out on. So here's the MNIST data set, mixed NIST data set. They're handwritten digits, 0 to 9. They're 28 by 28, really small. But 28 by 28 in the pixel space is 784 dimensions already, right? So this tiny thing has 784 dimensions. 4K TV is about 9 million dimensional pixel space, right? So to find something in a 4K TV image, you have to be able to navigate in 8.8 million dimensional space, right? That's computationally difficult, and who can even imagine it, right? So why care? The point is, why care? And this is the reason. It's because these interesting relationships in networking and everywhere else really live in these high dimensional spaces, and the signals are inside there. So there's a hitch. Let me show you this quickly. It's called the cursive dimensionality. It's a famous thing in statistics and machine learning. And basically, you can see it here. What happens is, suppose you have a linear thing, 1 dimension, you have 10 spaces, you have 1 point. So you got 1 in 10, right? Now, if you put it into 2 dimensions, now you got 1 in 100. You put it into 3 dimensions, it's 1 in 1,000. So what you can see is that the space is growing exponentially in the number of dimensions. And you guys know that anything that grows exponentially, it means you're in trouble somehow. So you have to stop that or learn how to do something with that. And so the space is growing exponentially, but there's this other problem too, is that things get stretched further and further apart so that everything's kind of equally far apart in very high dimensions. So you can't use things like, oh, this is further apart than that, and like a Euclidean distance thing, because it just doesn't work anymore. So, if you need to have examples from everything in your space, then there's going to be an exponential number of them, and you're kind of screwed. And so these kind of representations won't scale and won't get us what we want. And then, you can kind of hope for all kinds of different alternatives to this. Like you could use Mechanical Turk. Does anybody know what that is? It's like you get people to do tasks that only humans can do, and then Mechanical Turk, like type Mechanical Turk in your thing, and you'll find that Amazon has an auction site for people to get pennies per thing they label. You can use deep learning, which is what we are using, and all kinds of other aspects of that. But this is a big problem. So it looks like this. You can see it this way. Sparsity becomes exponentially worse as the dimensions go up, so things are harder to find. You can just think about it as there's a point somewhere, and as the number of dimensions go up, you got to search through an exponential space to find it. Okay, how much time do I have, by the way? 15 minutes? Okay, we'll try that. Okay, what's machine learning? Well, this is Andrew Ng. He's is a professor at Stanford. He was the guy who started the Google Brain project that built the cat detector, if you know about that. He's now at Baidu and Stanford. He was also the co-founder of Coursera. This is what he says. He basically says machine learning algorithms are simple, which they are in principle, and the complexity and the structures in the data in machine learning is about how to find that complexity or how to find that structure. And if you say it another way, you kind of imagine that there's a data generating distribution. Somehow there's some process. It's generating this data, like whatever's going on in your network is generating this. You're trying to find that. You want to learn that. And you care about how accurate the generalization part of that is. So you have training data, which you try to learn from. You don't really care about the accuracy on that because you can just memorize it. What you care about is accuracy on examples you haven't seen yet. You want to be able to predict the future or things that you haven't seen, not the ones you have seen. So there's all kinds of mathematical pitfalls, with the most notable ones called overfitting. So here's a cartoon of this. So in traditional programming, you get some data. Okay, packet comes to my router. I process the packet. I forward it on an interface. So I got data, I got a program, I get output. In machine learning, you have data and some description of what the output is. That's how you learn. And you output a program, right? So this, machine learning, learning in the machine learning setting actually outputs a program, code that runs on a specialized abstract machine, which might be a neural network or something like that. But this right here, people in our industry aren't really getting this yet. These things write code. So if you're in the business of writing code, you might want to think about it. Let's see. I don't know if we're gonna. Wow, let's skip all this. Feed-forward neural network. Okay, here's how a feed-forward neural network works. This is a little bit of math, but just bear with me on this. So here's how these things look. So on the left side, on your right side, there's inputs. So this is that vector. I said they're measurements from your network, right? SNMP, MIBs, whatever. What you do is you input that to the neural network, and it has what are called hidden layers. And these are layers that do computation. So where it says hidden layer 1, hidden layer 2, basically you process it and send it forward. Now, how does it process it? That's called forward propagation. How does it do it? Well, so this is one of those things blown up. So basically what it does is it takes all of its inputs, computes the weighted sum of those, and then just applies some function. And that function, activation function, is just some tiny nonlinearity. I'll show you. These are the kind of ones you use, like sigmoid, which squashes the input into the range 0, 1 if you have probabilities, or rectified linear, which goes 0 to the max, and things like that. And those things just feed to the next level, and it keeps doing that. And then at the end of it, you get the output of that, what's called the hypothesis, which is misnamed. It's just computing a function. And so where do these weights come from, right? That you, in the linear sum, that's where the learning is. All of what you know is in the strength of the synapses. They're weights, right? And these weights are what you learn. So that's what machine learning does, is it learns these weights. And so learning. You gotta, basically what you do is you get what's called a error function, and what you do is you just minimize the error that you get. And that's how you learn, right? So when you're learning something and you know the answer, your brain really doesn't do anything with that. Because if so learning is sort of error-based, right? You need to make errors in order to learn. That's a kind of a profound thing. I used to always tell my kids that, and they never believed it. But anyway, what you do is you try to learn from the errors, and then you propagate the error signal back through the network, and you adjust these weights until the error is minimized. That's the whole thing. That's why Andrew Ng was saying, in principle, it's simple. That's all it does. This is a picture of the error surface. And the reason that's interesting is because you want it to be convex, because you're going to try to find the minimum error. And if it's convex like that, you can just follow down what's called a gradient, which is a fancy name for the derivative of a vector, to the bottom of that. So if it's convex, you can do that. If it's non-convex, you can get lost. That makes it harder. The unfortunate thing is that all the interesting error functions are non-convex. So that's a whirlwind tour through that. So here's a little bit about what we're trying to do. Not so much Brocade, but in the industry. Or we're trying to build this discipline for networking right now. We're kind of inventing this discipline. So if you look at a sort of a ML stack, a machine learning stack, it kind of looks like this. At the bottom, you have this team of people, in my case, one, who basically their job is to collect the data and clean it up. That's a huge task. It's 80% of the work. And then you have this infrastructure to absorb it, ingest this data and all this stuff. And then you can do all kinds of interesting things with it, but it's a long time before you get to do machine learning. That's up at the top. So this is kind of what it looks like, and we're working kind of up here. We're trying to use standardized technology at the bottom, so like we're using Spark, other things like that. You can turn it on the side and kind of look at a workflow. So the analytics platform is like this. You got to collect the data, ingest it, all that stuff. You pre-process it to make it look normal and something that you can use. Machine learning is over here. You build a model, you generate something, I'm just calling it an oracle, but something you can ask questions to. And then over here, you can get intelligence, right? You ask questions to whatever this model thing is, and you use domain knowledge to make sense out of it, right? And you can do things like, topology, anomaly detection, root cause analysis, all these kind of things you want to do. And then you might do remediation or optimization. So if there's a problem, you might want to fix it. Or if there's optimization, you might want to optimize it. So what's this NFV stuff is all about optimization. They need to be able to do this. The problem is, and there's feedback all around in this, right? You have to continually feedback everywhere. And you have to apply domain knowledge. So you're not going to get people who aren't network experts who are going to be able to build this. You guys are going to have to be able to, be the people who build this, because domain knowledge is critical in this, right? And the thing is, it's going to be a while before, anybody lets something like this configure or optimize their network. So use something called a recommender system, which is related to what Netflix uses or Amazon uses to figure out what book you want to buy. But basically what it does here is just open the loop so you can put a human in. So this is kind of a workflow. So here's a simple example. So we wanted to build some tools for DevOps that would provide, kind of new kinds of automation and insights, primarily in the management plane. We use two algorithms, frequent pattern mining and k-means. These are really low-powered algorithms compared to what's out there. And let's see. Now let's forget that stuff because we're out of time. Forget about what these are. I just want to show you the inference. Where is it? Oh, okay. So what happens is this frequent pattern mining finds patterns in what are called categorical data. Categorical data is data that doesn't have an obvious relationship in ordering. So for example, if you have a flow record, is UDP greater than TCP? No, they're not related in that way, right? So this is called categorical, right? And so you might have a set of items that you get back from this pattern matching thing that looks like source, destination, source port, whatever, whatever you want to put in there. And by the way, you can put other stuff in there, like stuff from Chef and Puppet and all, whatever you want. So you get this set of transaction IDs corresponding to some pattern. And then this k-means algorithm can find clusters in other kinds of data. So, how data fits together, what things go together, right? And so a cluster can be like a set of transaction IDs that have congestion if they're flow records or something like that. And so it looks like this if you try to visualize it. These TID sets or clusters wind up looking like this. I just did a projection because it's in higher dimensional space. And if you're wondering why the green and the red are kind of overlapping, it's because when you have a higher dimensional space and you try to project it down into something you can actually look at, like a graph like that, it smears out a little bit, right? But here's the thing. If you have both of these, and these, by the way, these are just really simple algorithms, you can build something like this. So I get a set of these transaction ideas from pattern matching, pattern mining. I get some from k-means, and if you intersect those two sets, what you wind up with patterns that cluster together. So by the way, something like this, these application patterns will occur with congestion. So now you know if you can configure this, set of whatever they are, say it's some applications on some server somewhere, you can say, hey, if I do this, there's some probability, because this is machine learning, so it's all probabilistic. There's some probability that I'm going to get congestion over here. That's kind of an inference that really hasn't been seen before. And you're only limited by your imagination with this. So that's we built this. You can do it. You can actually do this. So how hard is it to build any of this stuff? Okay, here's some code I wrote, but that's the whole thing, really. Once your data is in the shape it needs to be. I wrote it in Scala because Spark ML Live has it, and I hadn't written anything in Scala, and I wanted to try it. So that's what it looked like. It wasn't that much. All that code's right there if you want it. For k-means, it's just this, not that much. So you can look at on my GitHub thing. It's all there if you want it. Let's see. Okay, so obviously we need data, and there's lots of engines to process it with. That's not interesting. We collected a bunch of stuff, like I said, all of this stuff, environmental sensor data, everything. We built this pipeline, and this pipeline did things like I was just describing. We can talk about it. But we're really only limited by our imagination on this, and we built a bunch of different things, but as soon as we saw we could do this, we started thinking about all these different things, and there's hundreds of those kind of inferences that you can make. But what's more interesting is that you can use this in a predictive way. So what you can do is you can say, this ACL or routing or QoS change will cause some kind of event with some probability. So like you could say, if you configure this application with these parameters, you're going to get congestion with this probability. That's kind of nice. You can do it, you can correlate real-time events with the same thing. And you can also use it to train other instances. So you can detect analogies like this, right? So it's pretty powerful, and you can make it all streaming in real time. Once you train the model, you can make it real time. Okay, so let's stop this. Let me see if I can get to the end of this. Anomaly detection is interesting. Oh, yeah, let me show you this. We built this anomaly detection thing, and then we just shoved it through this radial nested block state model graph thing. This was just the kind of graph that you have inside R, that kind of graph. And this thing came out, and we were all shocked because what happened here was there's about 3.5 million, no, 500 million flow records in here. These things right here, these are the anomalies, right? And this just popped out of that. So you can actually, the graph itself is the standard graph, right? But this is a way to visualize it. And these things were anomalies that hadn't been detected before. One of these was, I think, a SYN flood. And this one, we don't really know what it was, but we worked out on it a little bit. So there's some work we were doing on this one. But the guys who own this data didn't find that one because they used more conventional techniques. Okay. Oh man, I'm right on time. So what's the future? These things that have been so successful in perceptual tasks, the things that are driving cars and all of that stuff is going to start taking jobs away from people in your industry. That's what I'm saying. So heads up. That's happening. That's going to happen. This is taking jobs away from everybody, right? The interesting thing about machine learning, by the way, is standard automation, like factory automation, that was taking out people who were at the bottom of the thing, like I worked in an assembly plant or something. Now they're out of work because there's robots. Machine learning takes people out at the top, doctors, lawyers, things like that. It's very different. So keep your eyes open. This stuff is extremely powerful. I mean, I'll tell you, I said earlier, I think I've been around technology for a while. I've never seen anything as powerful as this. Like I felt like Han Solo. Never seen it. But never seen anything as powerful as this. And actually the tech is really cool. Everybody I know who sees this, especially in the networking domain, wants to work on it. So remember, these things are really powerful. These deep neural nets learn a computation, not a pattern or a statistical thing. They learn how to compute. What we're going to have in the future, well, we're already working on this, but more emphasis on control. So if you think about image processing, that's pretty static, right? You have an image, you try to segment it, find the things in it. We want to be able to analyze sophisticated long time series because network data is all time series data. It's very complicated and very highly structured with long range time dependencies. So we've been working on this right now. This is one way of doing it, which is what's called reinforcement learning, where you have just a simple scalar error signal. And I think machine learning is going to be doing unexpected work, unexpected network tasks. I'm calling this, I don't have a good acronym for this yet, but CSNSE, compute, storage, network, security, and energy. You have to have all of those things working together. Who thought we were going to have self-driving cars now? Or this close? Oh, these networks already write code. So if you're in the business of writing code, you might think about it. The weight matrix I was talking about, the thing that you learn, that's code. So those are where those weight things are. This also solves a problem that most frequently can't be solved by human programmers, which is called the selectivity and variance thing. You want to be selective, but invariant. You want to be selective to the things that you care about and invariant to the things that you don't care about. So for example, right now, there's not an obvious way to write a program that recognizes speech, but these things do it really well. They can write a program that does that. And we're just going to see progressively more machine learning and networking, predictive and reactive roles in management, control, and data planes. And this is just going to change the nature of the way we build and operate networking. And as I mentioned, there's a recent research group. I'm a little bit down on the IRTF. I don't know if anything will happen there. It'll be interesting to see if it does. And I'll just mention that we're at the very beginning of sort of some kind of network intelligence revolution, evolution, explosion. And if you look at where this stuff has taken hold in any other industry, there's just massive arms race going on in the hyperscales, in the automotive industry, anywhere where it's taken hold. So we're going to see that in our industry probably within the next year or two, I would guess. So that's a heads up. Whirlwind tour.
Fascinating stuff. I don't know if our post-social heads could take it all in, but are there any questions from the audience?
Yeah. Anytime anybody wants to talk about this, you probably can figure out how to find me. DMM at about anywhere. Patrick.
Yeah, hi Dave. I've been working together and talked about this kind of stuff. I think this is really cool. So being a person that actually has been doing some math once upon a time, even though I hardly remember, can you explain how we have managed to reach this space? Because you talk about this multi-dimensional sort of data set that grows exponentially. If you look at the reality, people have known for many, many years that is actually not the case, that it grows exponentially, because if you look at any kind of sort of video encoding use like H.264 or whatever, you actually have you already detect sort of the deltas between the frames, which means that if you, for example, do an edge detection, there's quite a lot of that happens around where the edge is, regardless on what dimension you go, which means that you don't really have to do the calculations all over the picture. So if you look at, for example, do sort of analysis of a video stream, for example. So my question to you is it that we have been able to do silicon and computation enough so that we have managed to do the calculations we need, or is it the theory around how to find sort of to draw detection, or let me just say, that we manage to understand how to do math and Fourier transforms or whatever over a large amount of data sets? Or is it these theories that have been optimized, or is it just all three things that have sort of met? What is it that has happened at this point in time? Because there are multiple things that happens, right?
Yes, so that's an excellent question. So first off, nobody codes up an edge detector in these things. They learn it themselves. So if you look at these neural networks, the bottom layer of this convolutional neural network, the first hidden layer they call it, that thing learns what are called Gabor filters, what your brain uses to do edge detection. Nobody codes that up. It learns it itself. So now what happened? Well, three things. One was, prior to 2006, people didn't really think that you could train deeper neural networks, which you needed to, because the deeper the network, the more complicated function you can compute, basically. And people didn't think you could train them because they'd been unsuccessful in doing so. And there were some theoretical breakthroughs that made that possible. But in order to train these things, you need a massive amount of data. That didn't exist before Google, Facebook, Baidu, whatever. So that's one thing. And then the second thing was just raw compute power. Training these things is massively parallel. You need lots and lots of cores. Like if you think about the Google cat detector thing, that was an Andrew Ng thing, was one of the biggest models ever built, had a couple of billion parameters. What they did was they ran it on 10,000, it was Google, so this is kind of prior to when people were using cores on GPUs. So it was Google. So they had 10,000 servers, I think it was 6 cores per. So they had that many cores, and that's how they trained it, right? And it took a couple of weeks. So, it's the advent of theoretical breakthroughs, compute, and data. All three of those things together.
Including what you started to say when you said that we are now doing learning. We don't have to apply the traditional sort of filters or anything to do edge detection and stuff. You just
learn those.
You just threw the raw data and it will learn.
It learns those. Yeah.
Okay, cool.
Yeah.
So you actually have evolution in all these different kind of things that sort of meets now.
Yeah.
Cool.
So
Thank you.
You don't code those up, in other words, right, Patrick?
Any other questions?
So you're working with Brocade, right?
Yeah, as far as I know.
Yeah. So will this? I mean, I realize this is early on in the field, but I mean, do you see a product coming up on the horizon? I mean, you were talking about anomaly detection. That's probably something that you could make a product out of.
Yeah, that's a great question. The product management people send me about 50 emails every day asking me when we're going to productize some of this stuff. And I usually say as soon as I can figure out how to make it work, But no, things like anomaly detection, now that's one that everybody's going to productize, and I hope we can get there. But you might ask a question about something like that. It's like, why not just use an IDS? There's IDS technology has been around forever, right?
Right, but how do you teach that?
Well, what's the answer? What's the answer to why? Let me ask the question and then answer it, okay? So the question is, why do I need machine learning when there's an IDS around that I can use, right? And here's the answer to this. What's inside the IDS? Well, what's in there is rules and fingerprints and maybe reputation data, things like that. Now, when you think about that, what that's really doing, if you zoom back a little bit, what things like rule sets and fingerprints really are doing is they're taking an input space, which is whatever the IDS is looking at, that high dimensional space I was talking about, and it's basically trying to tile that space so that I have a parameter set that will recognize each one of those different kind of events, right? In order to do that, I need to have a set of parameters for each of those tiles, right? Now, if the function that's really in there, which it always is all curved up and things like that, it will take an exponential number of parameters to tile that space. Not only that, you need an example from every tile in order to detect it. So if you have an IDS and you have a bunch of rules, but you get something that you've never seen before, it won't see it, right? Because you don't have a rule for it. Now, in the case of machine learning, remember I was saying it basically in the vision case, what you do is you build up these images by composing simpler things. So in the case of machine learning, you could say something like, I'm going to make this up, so it might be rough. But so suppose you have a picture and you recognize that in that picture there's a man and a dog in a car. And then you see a dog in a car with, with a boat. Now all of a sudden you can say, oh, man with boat, because you know what a man is, you know what a boat is, you can compose those. So now you can say, oh, I can recognize patterns that I haven't seen before, which is the real magic, right? And so machine learning can do that, and the IDS can't because it has to tile the space. So that's the real reason. So that's why everybody's trying to get to machine learning for anomaly detection, because you cannot tile that space, and you can't see every example because there's an exponential number of them. Now, what's the problem? The same problem with IDSs, false positives and false negatives. So you have to do some more work before you're done with that. But that's what it is, right? So it's really a question of what is the structure of the problem that's embedded in the space that you're looking at. Does that help?
Yeah, a bit, I think. Thank you.
You didn't convince me. Ask me later.
We'll talk more about this.
Okay, great. I'm sure you can all catch Dave during lunchtime and bombard him with all the any other questions you have. So fantastic talk. Thanks a lot for that.